Imagine you are right in the middle of preparing dinner. The ingredients are prepped, the pot is heating up, and suddenly, the flame sputters and dies. You are out of gas. Finishing your meal now requires tapping into a massive industrial supply chain. You are suddenly reliant on heavy, pressurized steel cylinders moving through a weathered, physical logistics network to get energy back into your kitchen. When that delivery network falters, a modern kitchen becomes a collection of useless surfaces. Without a continuous fuel from the outside world, you are effectively pushed back to a time before modern utilities, unable to boil water. This means that your ability to cook on demand is not a standalone feature of the house. It is a temporary lease on a complex external logistical system. If you try to replace that missing gas by simply lighting a makeshift wood fire in the backyard, you will likely end up with charred, ruined food. This chart compares the jagged, unpredictable peaks of an open flame to the steady, flat line required for cooking. Generating raw heat is easy, but maintaining a consistent temperature curve is a significant thermodynamic challenge. An uncontrolled fire transfers energy too aggressively. The leaping flames scorch the exterior of the food long before the thermal energy can penetrate and cook the center. Stove technology evolved to act as a governor for fire, translating the erratic bursts of a campfire into a predictable, mechanical tool for energy transfer. For most of history, cooking was a labor-intensive process. It required chopping wood and physically tending a large outdoor fire to keep a pot boiling. Raw wood fires also create immediate environmental penalties. You have to manage unpredictable flare-ups while working through thick, blinding smoke that requires constant fanning to keep the combustion alive. Charcoal represented the first major refinement to this process. By pre-burning wood to remove volatile gases, humans created a fuel that eliminated active flames, leaving only dense, glowing embers. This diagram shows the mechanics of radiant heat. Notice how the embers release energy in straight, upward vectors. This uniform delivery cooks the food evenly, avoiding the direct scorching caused by the chaotic movement of a flame. While charcoal stabilized the temperature, it still required significant manual effort. The cook had to remain at the hearth, fanning the coals to maintain the specific oxygen flow needed to keep the embers hot. The transition toward more manageable heat led to the development of stoves that utilized liquid fuel and wicks as an interface for combustion. In a kerosene stove, wicks draw fuel upward into this metal burner assembly, sustaining a flame at a consistent height. Switching to liquid fuel meant you no longer needed to haul wood, significantly reducing the physical labor of maintaining a kitchen fire. This technology eventually led to the modern gas stove, which achieved smokeless ignition. Looking at these 5 dials, you can see how precise heat control became a matter of mechanical adjustment rather than physical exertion. Gas and liquid fuels achieved high levels of control, but they also cemented the kitchen's reliance on the industrial networks we saw at the start. This led engineers to ask if cooking heat could be generated without using pressurized gases or the act of burning anything at all. This diagram illustrates joule heating. As electrical current moves through a resistive wire, the friction of that movement generates heat, turning the coil glowing red without producing a single spark. This setup changes the safety profile of the kitchen. While it removes the hazard of an open flame, the fully enclosed design hides a new set of risks, like electrical shorts and potential electrocution. By replacing fire with electrical resistance, this technology removed the need to burn physical fuel in the home, moving the actual combustion process to a distant power plant. If electric and gas stoves are more efficient and objectively safer, why do we still deliberately choose to cook over charcoal and wood? The reason is chemical. As wood and charcoal burn, the smoke releases complex aromatic compounds that settle on the food. These flavors are physical byproducts of combustion that an electric coil simply cannot produce. There is also a psychological draw to the traditional hearth. Unlike a single modern appliance, a wood-fired stove creates a wide communal focus, requiring people to gather and work together to prepare a meal. Engineering has optimized our stoves for speed and safety. However, our preference for specific flavors and shared environments ensures that the original campfire remains a part of how we eat.